Right.
Oh my God.
So welcome everybody to the second day for the CO2GeoNet webinar. As you saw from the pop-up, we are recording this because we hope to post it later on the internet with the permission of the speakers. Quick announcement, we are going to run over a little bit today on purpose for once. We managed to locate our missing speaker from yesterday, so Darren is very kindly going to join us at the very end of the session at 4:30 for a very horrible time for Australia, but very much appreciate him coming on board for today. So welcome everybody. I'm looking forward to the event today. I think we've got some really good speakers lined up, and in order not to delay us any further, I'm going to hand over to Paul to give our keynote presentation. So Paul, the floor is yours.
Thank you very much. And good afternoon, good morning, or good night to all of you, wherever you are. Let's just say that if any one of you would like to show your face, then I'd be delighted to see you. But I understand if you want to do other things as well. But speaking into my own little face is kind of getting on my nerves. And there's Isabel. You know, that's so wonderful. I left the CCS scene a long time ago. Hi there, Rowena. And it's so heartwarming to see that some of you guys, you're still there. You're still fighting for CCS. You know, we started the ZEP platform, the zero emission platform, way back in 2000 and what was it, 6 or 7? And we really got upscale in 2009, where we had this announcement of the up to 20 full scale. We were a little bit ambitious, but the German Chancellor said it, the European Council said it, and we were really up there in full speed. And we had the NER 300, and we had the directive on geological storage of CO2, and we were all set to go. And obviously then we were hit by financial crisis, and the price of ETS fell, and well, the whole debacle. And I'm not going to dwell on that debacle. I just want to say that, wow, it feels good to be back, and wonderful to see so many familiar faces, because this is a struggle. Interestingly, what's interesting to be outside for a while is that you come back and you see things with different eyes. And I'm no longer speaking on behalf of Bellona, that I left some 9 years ago. Today I work as a consultant on energy and climate policy, predominantly on European issues. I'm an advisor to some Norwegian companies who are very advanced in the energy transition work. And so I've been able to work on other sectors because we became a little bit closed-minded with the CCS after a while. And it's been wonderful to see how CCS fits with all the other energy sources and the policy issues. So, dear friends, I have 2 messages for you, all right? Because there are 2 things that I think are important in order to, as we now take advantage of this momentum, because there is a momentum here. I mean, the 2030 goals of first the Paris Agreement, and then the 2030 goals of the European Union, Fit for 55, etc., is going to make and then give us an enormous sense of urgency in developing CCS technologies. And Norway, with its Longship, has made a huge advancement, and there are some very interesting other projects around in Europe and indeed in the world. But we are not there yet, because we are still faced with this criticism that it's a waste of money, it takes too long time, technology is not tested. And I recognize a lot of the old arguments that we had 10 to 15 years ago. And so we have to, I think, learn from that. And here's my 2 5-sense learning things that I think are important. The first thing I think is that, and this is not new to you, but I do think that the whole issue of carbon negative or climate positive or whatever you want to call it is an asset, and that's something we should really lift, because CCS with sustainably produced biomass is an undisputable solution if we want to reach climate neutrality. And the whole term climate neutrality means that there's some parts are going to still let out CO2 and some parts where we have to go negative. This technology is obviously well known, but what we do lack, and there is where I think we need to put more effort, is to develop those commercially viable value chains. I mean, the IEA is hammering on us, do CCS, introduce policies, yes, but we're all aware of that. But as long as it doesn't make money, it's never going to work. And it's only Norway who has the money to pay for all this, plus the innovation fund that can give some support to projects, hopefully, that will get them started. But every country is not Norway, and we can't pay for everybody. So we have to create some sustainable, some commercially viable value chain. How do we do that? Well, I think there needs to be a discussion of how much you value storing captured biogenic CO2, right? Because when you do that, you actually remove CO2 from the atmosphere. And oh my God, the European Commission, are you here? How long have we been talking about, we got to get this into the guidelines of the ETS? I mean, we just got to do that. We've been fiddling around that for too long. Let's just, get that done and allow for a mechanism where we can reward. That's one option. I know Swedish authorities are actually working on that, and we need to engage with those governments who are actually thinking in these terms. One way might be to say, right, you pay a certain price to emit a ton of CO2. Well, if you withdraw that ton from the atmosphere, you should be rewarded equally. So you get an extra, not even a bonus, but an extra payment for storing biogenic captured CO2. I mean, in Norway, we have a tax system that provides all kinds of advantages to drill up the oil and the gas. I mean, there is no limit to the kinds of advantages that you can benefit from if you drill for oil and gas. So we need to think in the same terms. How can we create those similar advantages tax-wise, and also in terms of emission trading scheme, that it becomes, you put the price on the CO2 that you can actually earn from. And so that's the first thing. And the other thing is we got to solve the problem of the sustainability of CO2. I mean, if we are not going to store the CO2, we will sell it and create industrial value chains that actually provide an income. And we for those countries who are not Norway rich, that needs to happen, right? We need to be able to sell the CO2 to produce fuel, to produce CO2 in Holland, in the Dutch flour business. We have to, there's all kinds of industrial activities that actually can take advantage of CO2. But if we don't solve the sustainability problem, it's not going to fly, because there's going to be opposition. And for once, the IEA was very, I shouldn't say for once, but here the IEA was very clear. And I think we have to come to terms with that you can only use the CO2 that is captured from a biogenic source, right? Because that is carbon neutral when it was emitted. And so if we capture it and use it in an industrial process, then it will not add to the CO2 emissions, right? But if you use captured fossil-based CO2, then the society is not going to accept it, because it's just, we're just delaying it. And, it's not so difficult to make that calculation. For instance, when you burn waste, to make that calculation, how much part of that waste is from fossil sources and from biogenic sources. In Norway, the environmental directorate has done a wonderful job in trying to calculate, and it's between 40 to 60, it's around 50%, 50-50. That should be a source that would provide societal approval of CCS that leads to a carbon negative solutions. Right. So my first point was create a commercially viable value chain using biogenetic sources of CO2, either to store it and to receive the same amount as you have to pay to emit it, or that you can sell to the market for industrial purposes. All right, sorry, I have another 5 minutes. My second point. My second point is, you know what, and this is a tough one, and a lot of people are going to shoot me, and it's so comfortable. I'm behind the screen. You can't do anything. I mean, you can put up a plastic gun or something and throw water at your screen, or you can turn off you can unmute yourself and shout at me. But let me say this. This must not be a fossil industry prerogative, right? This is very much driven by the oil and gas companies, and boy, we needed them. They had the experience, they had the geological knowledge, they have the know-how to, I got a SMS, I wonder if, no, that wasn't somebody saying, stop, Paul, because CO2 is a waste, right? And how do we deal with waste, right? We create a place to put it. And then we, the policy of the waste hierarchy is that you reduce the waste. So obviously the first thing is to reduce the emissions. But those emissions that we cannot take care of, we have to make that a sector neutral mechanism. And we need governments to take the initiatives to provide storage space where they can hire a petroleum company to do the storage because they have the knowledge. But it mustn't become an income stream for Equinor, Shell, and Total, and all the others. Obviously, if they are going to do this, they have to make money. I see that point, absolutely. But in terms of societal approval, we have to de-link CCS from the fossil industry as much as we can, and to spread out CCS on a really wide basis. It needs to become similar mechanisms as we have in the waste sector. You have a gate fee that you pay when you store, right? That gate fee can be subsidized. It can be based on volume. It can be based on purity. It can be based on a lot of things. But we have to then show that this is something that the governments take in their hands and provide a framework, just as they provide frameworks for the whole waste sector. There is nobody who complains when we actually manage the waste. When you do landfill, people complain, obviously. Some complain also when you burn from waste to energy, but there you have CCS. But it mustn't be that you hook on the petroleum sector at every stage. They will do their blue hydrogen. They will produce natural gas and capture the CO2 and sell the blue hydrogen to the market. But we need to have CCS on a much broader base. For industry, as we have seen, and as you shall see today, cement, steel, pulp and paper, and so forth. But it has to be a broader framework that the government set up to deal with the CO2, and you get market mechanisms such as the gate fees used in waste disposal. That is fair. Then it becomes a really environmental and climate initiatives that everybody can subscribe to, which does not play up to prolonging the fossils sector. which obviously people are concerned about. And that is the last resistance that we see to CCS. And we have to deal with that. And we have to be honest to ourselves that these are the issues that we face. Ceri, it's now 14:18. Shall I open up for questions or comments, or people want to shoot me? Whatever.
Yeah, if you're ready for it. I think we see some questions coming in the chat, and I think maybe we could invite people to raise their hand as well if they have a question, so we could have some verbal questions this time as well, since I think your talk could be quite provocative if you're open to that, Paul.
Yep, of course.
Okay.
I'm the openest person in the world. I would love to see people move their faces and use their voice and be as interactive as possible.
Okay, so I see we have a question in the chat. So in 2007, many oil companies did not want to work on CCS. What now? They always dictate.
Well, yeah, how can I answer that? Well, two ways of answering that. The easy answer is it wasn't commercially viable and it was too expensive. We didn't have a shelf technology available, and it was too costly. And yeah, they always dictate. Well, you know, money talks. They're very powerful. I mean, when I worked for Bellona, we worked hand in hand with the oil and gas industry to promote this technologies, this vital technology. It's just that it's so vital that it belongs to a broader community and then only the petroleum sector. And that's what I think is important, to gain that public acceptance of it. Who should take care of CO2 storage if not the oil companies? Well, yeah, WIT, that's the $48,000 question. And that's one of the things that I try to convey, that yes, those who have the geological experience is today petroleum companies. That is true. But we are in a way too dependent on it. There needs to be some kind of government initiative to say that, as we do in waste policy, again, I'm sorry, the government provides a contract with a company, and they fulfill their duty, their role. So I think that it should be, particularly due to the skepticism to storing CO2 onshore, which we probably won't do, but even offshore, the government needs to take a role to say, we have provided a field and we are auctioning out who can do this for the most rational and inexpensive way. And so but some petroleum companies will definitely be at the lead. Schlumberger, and there are other companies who will be able to do so. But I feel that we are too much, you know, I shouldn't say this, and I hope this is not recorded, but we're too much, in a way, to the first question, we're a little bit dictated, because they pull all the shots, and it's very difficult for us to find what are the real costs. You know, the EFTA Surveillance Authority, which is the most unknown international organization in the world, but they are the commission to Norway. They did a fantastic study on the whole value chain. It's the best I've ever read. And the thing is that in order to provide a green light for state aid to the Longship, the Equinor and all the actors had to provide the figures. And it was a fantastic study with all the figures, and you can see how much money they needed from the state and so forth, except that the figures were censored, of course. So again, we couldn't see. So we are searching in the dark. We're searching in the dark, and it cannot continue that way. It has to be transparency. It has to be a transparent public process where people have to say, this is what I was finally able to get it out of Equinor, that they will charge €55 for 1 ton of CO2 at berth. So they will fetch it at a harbor, bring it to the storage place, and store it safely 2,000 meters under the seabed for €55 per ton. Great, great. That's a huge step forward, but we need much more transparency, and we might need much more competition in that. And it's interesting to see that Denmark is now taking up picking up the globe and wants to create its own storage place in the Kattegat Sea. But as long as we leave it to the petroleum companies, it's really difficult to get the kind of transparency. That was a long answer to a short question. Another question.
I was going to ask you about value chains, because you kind of hinted maybe we should have different colours of CO2. We have blue and green hydrogen. Do we have different colours of CO2 that have different value because of how much they contribute to this climate change solution?
Yes, as the IEA very clearly says, you know, you should only reuse CO2 from biological sources. That's a green CO2. And so green CO2 would allow you to sell that CO2 in the market to get an income, to make it, to make money out of it, because we've got to solve that issue. We cannot only depend on public funding. But at the same time, fossil CO2 has to go into the ground. And I don't think that's such a difficult thing to make that distinction, but it takes leadership from the governments to say that, you know, this is the way forward. And they have to provide a remuneration, an incentive, an economic, financial incentives for storing biological CO2.
It's true, so long as it's cheaper to throw CO2 into the air than it is to do something responsible with it, that's what will happen. Yes,
and Ceri, you're on to something very, very important there. Thank you for bringing that up, because we've been waiting for the price of carbon to be more costly than the price of storing it. And I'm afraid that's like waiting for Godot, which is an Irish screenplay that ends with waiting and waiting and waiting. Because today the price of CO2 in Europe is 60 euro, which is starting to hurt a lot. And maybe, you know, we've been saying that it suffices, it's enough, but it's still not enough to get it. So we worked on this in 2009 already to set a limit, you know, to say, you know, how much CO2 will you be allowed to let out per megawatt electricity that you produce? You know, EP, what do you call it? Performance criteria. And you can actually combine that with the price of carbon. But again, that will take some leadership, and the industry is fiercely opposing it because, yes, it is a constraint. But, you know, the party's over. We need to deliver now. There's a sense of urgency, and we need to use the tools that are available to us. And emission performance standards is a very important tool that can get this thing started. And obviously, you know, the energy providers are not going to like it. But I tell you, the day the government has the courage to set that emission performance standards, you know, this sector is so powerful, so innovative, so resource. I mean, in Norway, petroleum companies can deduct 78% of the investment in research, right? So, I mean, there's a tremendous power if they have the right goals. But as long as we just, you know, play into them and say, well, we wait for the carbon price and, you know, we need to have some public support. And I'm sorry, been there, done it. We tried it in 2009. We tried it in 2012. We tried it in 2016. We tried it in 2018. We're trying it still, you know, and we are being laughed at. We are being laughed at. And, you know, CCS has a new momentum, and let's not miss this momentum because it might be the last one. Last question. More questions.
Okay, I don't see any in the chat, so I'm going to be cheeky and ask. So what do you see as good short-term mechanisms? You've mentioned the government showing initiative. I mean, what are good short-term mechanisms? Is it the demand for green products from society? Is it taxes? Is it some kind of incentive rather than the stick?
I mean, the Commission has for a long time been talking about introducing a contract for difference like they have in the UK. On a European scale, interesting. Will it work? Might work. Do we need it quickly? Yes. but we have to decide. We have to get into the starting blocks and say, all right, this is what we're going to do. So let's do it, right? ZEP has been arguing for this for a long time. But the governments don't seem to have the courage. And why don't the governments have to have the courage? It's not the government's blame, it's our blame. Because we're speaking with, we want a little bit of incentives, but we don't really want the incentive. So yes, we need to have predictability and clarity. And either you, as I said, you create a mirror ETS mechanism for storage of biological CO2. That's an option. You create very clear boundaries on what you can actually capture and resell and use into the market. And there has to be clarity, because people will not accept that we just capture fossil CO2 and move it into a value chain and let it out later on. It's just not going to fly. But as IEA says, the biological CO2, you can do that. Taxes, well, taxes is never popular, and no industry is going to ask for taxes. We're going to ask for incentives. And so again, the EP, the emission performance standard, I think is vital as well. The learning curve, we've been talking about this learning curve so long. We all thought that in Saskatchewan, in Canada, where Shell again has succeeded, but what happened? Why haven't we seen the second? All kinds of explanations. But we cannot pretend that we're going to learn and then make it 30% cheaper next time, because we don't have time for that. Another question, Ceri? Your questions are very good.
I was actually going to ask you about demand from society, because I was talking to some of my family members about climate, and they said, well, it's not me personally, it's all these big companies producing all these emissions. And I said, well, they wouldn't be producing the emissions if we weren't using the products. They're not just making them for the sake of it. So it is, and I have to say, I think the young generation coming up is very, very aware. And I really think that my generation is the last one that gets to wreck the place. I really feel optimistic about the younger generation, about societal change. And I really feel that the younger generation have really grasped the nettle on this one and are demanding something in a really loud voice. And I think as more of them get to voting age, their voice becomes even louder. Do you agree?
Yeah, oh, absolutely. I mean, Greta Thunberg and my own children, obviously they don't eat meat. They don't want to drive a fossil car. I mean, they're worse than I am. So yes, you're absolutely right. But the other thing is that we are, for instance, in Norway, we are meeting this criticism with the fact that all these emission reduction should come from a decrease in demand. Right? So we say that we can invest in CCS, but the demand for fossil fuel has to be the main driver for reducing the production. And that is a fallacy. And we have to, again, we're fighting huge communication departments in every huge fossil company. And it's very, very hard. It's very, very hard to break that chain of arguments because the demand. It's not only the demand side. There is a responsibility lying on the producers. I mean, how did we deal with cigarette smoking? We have traffic lights. We have look at aviation security. I mean, for every danger in the society, we have very strict rules. And climate change has not come to the point where we realized that it is so dangerous that we need similar mechanisms to deal with it. And that's why I think we have to step up, shift gears, and demand to be more bold. And we all need to be the bearer of that message. And CCS cannot be driven by fossil companies. You know, it's like asking Philip Morris to define the policy of how people should smoke less. We don't do that.
That's a really good way of looking at it, that it comes from all directions.
Yeah. So anyway, let's hope that the Atos project in or Portos, or which Musketeer was it, in Holland, will succeed. Let's hope that the Longship will succeed, and that they will actually, you know, we spoke so elegantly about cost reductions in 2009 and all these years, but we haven't really seen it. There are still PowerPoint presentations that give an indication of huge cost reductions as we do technology development, upscaling, and discovery, but we haven't seen it in practice. So price mechanisms and cost discovery, yes, but we need all of them. We need that and the predictable framework conditions that set clear goals for emitting CO2. That will get CCS going.
Thank you very much, Paul. And on this optimistic note and call for action, I'm going to thank you very much as our keynote speaker. And we're going to move into the next session on CCS. So Jannicke, I believe I saw you online.
Yes,
thank you very much for the attention. And good
Thank
luck.
you very much, Paul. Thank you. Thank you, Jannicke. So are you ready with your presentation to share your screen?
Yes, I am. Let me just get the full screen. And then hopefully you can see my screen now.
Yep, we can see you now. We can see your screen.
Very good. Thank you. Hello, everybody. Thank you for the invitation to speak here today. I will be presenting the Fortum Oslo Varme carbon capture project. But first, briefly about the company. Fortum Oslo Varme is, as the name says, an Oslo-based company, district heating, especially with the main load into the district heating system from waste incineration. We also build up in cooling to be able to provide both heating and cooling for large buildings in Oslo. So shortly about the context of this project. For those of you who attended yesterday, you probably heard about the Longship project. We are a part of the Longship project, one of two capture projects. The other one is on cement, while our project is carbon capture from waste to energy. And the main idea is to capture CO2 from two capture sites and transport and store permanently this CO2 in a geological formation off the northern coast of Norway, about 3,000 meters below seabed. Now, this is a demonstration project, and that's also why these capture projects are part of the full Norwegian full-scale CCS project, to demonstrate the whole logistics chain and the possibility of other CO2 emitters all over Europe to connect to the value chain and to deposit their CO2 at this storage place. And of course, also to demonstrate the capture process and that it works on industrial flue gases and that it is possible to condition and to send for transportation and permanent storage. A little bit more about our capture project. Up in the right-hand corner, you can see the waste-to-energy plant located just south of Oslo. The goal of our project is to capture about 400,000 tons of CO2 every year, and that is about 90% of the total CO2 emissions from this plant. The plant treats residual waste and household waste from municipalities surrounding Oslo, and also industrial waste, both from Norway and actually also from the UK, where the alternative for this waste, this residual waste, is landfills. So even with the transport, this is a very sustainable way of treating the UK waste, actually, reducing emissions to a large degree by avoiding the methane emissions from landfills and being able to utilize the heat from the incineration to produce district heating and electricity. This carbon capture project has developed through concept, through feasibility, concept, and feed phase. So we are basically fully matured this project, and we are ready to start as soon as we have the total financing in place, and that's what we are working on now. We delivered the feed report in 2019, and the Norwegian state has also quality assured this project. So basically everything is set and ready to go. This waste to energy plant is not situated at port, which means that we have to transport the CO2 from our plant to port. And this is also an important demonstration measure for European emission points to prove that it's possible and feasible to deal with your CO2 emissions, even if you're not situated directly at port. Now, we're planning to do this using emission-free trucks, preferably electric trucks, where Norway has come quite a long way to implement electric vehicles. So that's the main plan. During the feed phase, we also built and operated a pilot plant to test our specific, the chosen technology on our specific flue gas. We have chosen the Shell technology that Paul was talking about from the Boundary Dam project in Saskatchewan in Canada, where the technology basically has been proven, but this is on flue gas from coal power. Now, this is flue gas from waste to energy, and we wanted to make sure that we knew everything about the reactions between the flue gas and the amine solution, and that we had full control of emissions and capture rate and so on. So this technology has now been thoroughly tested through 9 months, more than 5,000 test hours on this waste to energy flue gas. And we have gotten really good results, very high capture rate, very low emissions, and stable operations. So we are confident that this capture plant will work and that it will be safe, because we are situated in the middle of Oslo, basically, with, as you can see from the lower picture, with residential areas very close to the plant. So this is, of course, of very high importance for the project. As Paul also touched upon was the importance of BECCS, or carbon removal. And this is something that the waste to energy sector can contribute to and to reach European climate goals, because about 50% of the CO2 emissions from this process is biogenic, which means that when we capture and store this CO2, we're actually removing CO2 from the atmosphere. So this is a very important advantage and a very important factor when addressing the emissions from waste to energy. About the financing, those of you who already know the Longship project, the Norwegian full-scale project, you probably already know that the project has reached its final investment decision with the Norwegian state. At the end of 2020, the Norwegian state decided to fully fund the transport and storage part of the project, and also to fully fund the Norcem cement carbon capture project. Regarding our capture project, we received about 50% of the funding that we need, conditional that we can find the remaining funding from external sources. And the Norwegian state was particularly pointing towards Europe and the European Innovation Fund for this additional funding, which means that we have been applying to the Innovation Fund, and we submitted the final application at the end of June, now awaiting the results from this process. We are positive, of course. We believe that we should stand a fair chance. Our project is fully matured ready to start as soon as we have the financing in place. Partially funding from the Norwegian state, and also with, as I mentioned, the transport and storage part of the project already funded and being realized. So this is important, of course. And also with the BECCS, or the carbon removal potential, this is an important capture project for Europe to demonstrate carbon capture from waste to energy and to demonstrate the logistics chain. We have applied for 180 million euros with the Innovation Fund. Well, I'll also mention that if we receive the funding from the Innovation Fund, we will find the remaining funding in dialogue with our owners and with the Norwegian state. And the plan is then to reach a final investment decision and start constructions by the first quarter of 2022. And this means that we can have the capture plant in operation at the end of 2025. So that's the goal we're working towards. And why is this project a part of the Longship project? Because that was also a discussion, of course, which industries to focus on for the Norwegian full-scale project. And waste is one of the biggest climate challenges in the world today, with enormous methane emissions, especially from landfills, where methane actually accounts for 20% of the global warming. So this is a challenge that we should address even stronger. And the closing down of landfills and the transition towards sorting and recycling of the waste that we can recycle is one of the most important steps that we need to make, in addition, of course, to phasing out fossil energy and to build out renewable energy. But there will always be a rest product, a part of the waste that we cannot recycle or that we want to take out of the cycle, and that we also need to treat in a sustainable manner. And that's where waste to energy is the most sustainable treatment of this residual waste. And by adding CCS to the waste to energy, we can deal with the CO2 emissions from this end-of-line solution for waste, and in addition, remove CO2 from the atmosphere. So this is something that needs to be developed at large scale in Europe and, of course, globally. This is how we want the future circular economy to look like, with raw materials in the waste going in a loop and being recycled in a circular economy. But with the arrow towards the landfills to be cut, and this waste instead to be incinerated in waste to energy plants with energy recovery and CCS to deal with the CO2 emissions. Some of the CO2 may also be utilized to add to the circular economy and to keep the carbon in the cycle. But we need large amounts of this CO2 to be stored, to be taken out of the cycle, out of the atmosphere, to be able to reach the net zero goal. And Paul has already touched about the importance of carbon removal, or BECCS. And just to emphasize how important this is, we know that we need to reach net zero, but that's not enough. We actually need to go carbon negative, because we have already increased the temperature. And in order to go carbon negative, in essence, this means that we need to remove more CO2 from the atmosphere than we release from fossil CO2. And that's where we need to capture and store and to remove this biological CO2, either with natural removal methods or with technical removal methods, such as CCS. And waste to energy as an industry can contribute to a large amounts of these negative emissions. And I'm getting close to the end now. Very quickly also, that we also need to focus on the fossil part of the waste, the plastic issue. We all know the challenges we have with microplastics and the challenges we have with recycling a lot of the plastic. Unfortunately, plastics is a difficult fraction to recycle, and today there is a lot of reject from the recycling process, in addition to all the plastic that is dumped or never sent to waste handling at all. And in 2015, only 9% of the plastics we were actually able to recycle. So this is a huge challenge, especially when it ends up in landfills and in our waters, rivers, and the sea. So waste to energy can deal with this plastic and adding carbon capture to deal with the CO2 emissions from the plastic. So this is important also for the fossil part of the emissions. Okay, to sum up, we need waste to energy in the circular economy to deal with the waste that we cannot or don't want to recycle. Adding CCS to waste to energy will also give negative CO2 emissions and contribute to carbon removal and climate positivity. And this project is also important for cities, as waste handling, circular economy, and the sustainable waste handling methods is an important part of cities' infrastructure. So this is an important project for the city of Oslo, for example, to remove the emissions and to reach their climate goals. Okay, I think I'll stop there and open up for questions.
Thank you, Jannicke. It's really good to be reminded that CCS is just part of a larger value chain, and it's slightly horrifying to see how little plastic is recycled and how much waste is still present in the system, and how much, even though we've made great movements on recycling, that the problem hasn't gone away. And I think that's really good to be reminded of that. We have a quick question in the chat before we move on to the next presentation. Can this capture from waste be extended systematically to all municipalities? What would it take in terms of incentives?
Well, yeah, I definitely think it could be extended, and that's also something that we are working towards, to be this demonstration project and to be the starting point for a learning curve and a cost-cutting curve for the next projects to come. The technology that we will demonstrate is directly replicable to similar plants all over Europe, and we're also working with the technology providers to develop modular solutions, solutions to basically be able to offer carbon capture as a service, and I think this is going to develop quite quickly, actually, because we see that the sector and the industry is now interested. It has a lot of the plants, both in Norway, in Scandinavia, and also several places in Europe, has now started their own projects. So this is really, the ball has really started rolling, and I don't think it's going to stop. So this is going to come, but we need regulations, we need legislations in place for this area, and especially addressing the bio content, as Paul was discussing as well. We need to have a framework and to find a way to certify this bioshare and the removal of the carbon, because that's what we do when we capture and store the biological CO2. So by doing this, we can develop a market, and we already see private initiatives developing this market. And in order to accelerate this framework and legislation will be extremely important to accelerate the development.
Thank you very much, Jannicke. Okay, we're going to move on to the next presentation. Thank you. That was really, really helpful and really informative. So thank you very much for this presentation. So we're now going to move on to another developing innovation for CCS, low carbon cement. Alla, the floor is yours.
Okay, can you see my presentation?
Yes, we see your slides.
Okay, this is a presentation from the Horizon 2020 project clean clinker production by calcium looping process. And this is large project, results from many partners. So, sorry, I have number of points. Don't know if I'm able to speak about everything. I will try. So generally, the project started in 2017, and now it is extended for 6 months because of COVID, and it will finish next year. So we have 13 partners from 5 European Union member states, and also participants from Switzerland and China. The project includes 8 work packages, and most of them devoted to the calcium looping capture in the cement plant. And we have 1 work package, 7 on CO2 transport, use and storage, which I'm leading, and our university, Tallinn University of Technology, is leading partner in this work package. So the ultimate objective of CLEANKER project is advancing the integrated calcium looping process for CO2 capture in the cement plants. And the targets were to demonstrate calcium looping process at the TRL7 in a new demo system connected to operating cement plant in the northern Italy in Vernasca cement plant, operated by Buzi company. To demonstrate techno-economical feasibility of the integrated calcium looping process and to demonstrate the storage of CO2 captured from calcium looping demo systems through mineralization of inorganic material in pilot reactor of 100 liters to be built in Vernasca. Now we are building 200 liters already. And also project has another objectives, but I will speak only about this main. And if sometimes also about work package 7 on CO2 use, transport and storage. So this calcium looping is a relatively new process proposed in 1999. And calcium looping is generally capture processes at the cement plants. They are different from the capture processes in power plants, and it is some kind of oxy-fuel capture, but for oxygen transportation there is calcium. So generally it consists of 2 processes, one of which is carbonation and another process is calcination. And both are at the high temperatures, 650 degrees Celsius and 900 degrees Celsius. And so this is more details for this process. So this is equation for calcination, which is at the very high process at the very high temperature, and carbonation at 650 degrees. So generally some more details of these technical parts. Of course, I am not capture expert, so all this made by my colleagues, project coordinator and other expert and capture partners from our CLEANKER project. This is some more indicative configuration of the pilot, which were prepared by engineers and experts and researchers from our project for demonstrator. And this is our project timescale. Generally, we already had erection of pilot demo plant. I will show pictures. And in this year, we have to complete casting of concrete together with captured CO2 and all final conclusions, and we have to finalize project next year. So this is some figures from CLEANKER demo system from Vernasca cement plant. This is demo. Yes, this is just pictures to see all this very complicated, and this is already opening event of this pilot demo last year in October. So unfortunately, because of COVID, this opening was made only at the national level, and only Italian partners took part and some German key partners. And we could not take part in this opening event because of COVID restrictions. So the project includes 9 experimental campaigns planned, 5 short tests of 3 days, and also 4 long tests, 1 week each one. And the aim of this test to analyze different parameters, including oxidant for the calcination process, outlet temperature, type of CO2 sorbent, gas flow rate, solid to gas ratio, and solid temperature at carbonate inlet. So because the time is really very limited, so I want to tell a little bit also about work package 7, which we are coordinating with CO2 transport, use and storage. And in this work package, we had different objectives, but I will show you already some results. We already made most of the tasks, including methodology, techno-economic modeling, regulatory issues, then cluster. We proposed cement plants to the worldwide ongoing cluster projects to be for calcium looping exploitation study. And now we are one task on mineral trapping is ongoing, and the testing of carbonated materials for use in concrete will be for the next year, I think. And also in this project, we had very extensive education activities, and only in our university, we prepared 5 master theses were defended in our university. So 2 on mineral carbonation, and 2 on geology, starting 1 in 2018, and the last one in 2021 on cluster projects in United Kingdom. And 1 master thesis was made in cooperation with NS project about North Italian scenario for the cement industry. And this was made by Italian student Martina Mariani. And so we had in the project, it was planned to make techno-economic modeling for 2 scenarios, 1 regional Baltic regional scenario and 1 local Italian. But we made even more. For Baltic scenario, we made 1 offshore scenario, innovative synergy scenario with renewable energy. And in this scenario, we made only technical modeling, geological and technical modeling. And another scenario, which is onshore scenario, we made full techno-economic modeling. And this scenario includes 6 CO2 emission sources, CO2 use for mineral carbonation plant using oil shale ash from Estonian energy production, pipeline transport, storage in Latvian structure, and storage reservoir is Cambrian saline aquifer, Demian formation sandstones. And we made all economic estimations. So we just heard from our Norwegian colleague from Paal that we have to pay, if we make storage in Norway, only for storage, we have to pay 55 euro per ton. Yes, of course, if we make local regional scenario and onshore storage, we have another costs. And for example, in this scenario, we got that if emission allowance price will be 40 euro for ton CO2 and 50 euro for ton CO2, then even at these prices, this CCS scenario could be beneficial for 3 Eesti Energia and Latv Energia power plants, because Eesti Energia will also apply CO2 use and will get benefits from this, from byproducts. And Latvian Energia, because located very close to the storage site. And the emission sources Kunda Nordic Cement and VKG Energia, they are without CO2 use options, located not so close. Then they will need 50 euro per ton CO2 in order to cover all CCUS costs, including capture, compression, transport and storage and monitoring. So you can compare that Norwegian offers only for storage 55 euro. Okay, and also we made one interesting study worldwide. The task was to propose cement plants for our partners, Heidelberg Cement and Buzi Unicem Cement, propose cement plants which is located the most convenient and could be used for exploitation study and could be integrated in the worldwide clusters. So generally, we mapped 12 clusters worldwide and proposed for all these world cluster projects cement plants from one or from two companies available there. And end of December 2020, we sent a letter with extended abstract about this study and proposed them to integrate which cement plants are better to integrate. And after our proposal in 2021, Heidelberg Cement, British subsidiary Hanson UK, has become a partner in the HyNet Northwest Consortium and include Bateswood Cement Plant, which we proposed after our study. So I think that we're already very happy that our results have very practical, our research have resulted in very practical things which were made by Heidelberg Cement Company. So, and also one scenario was North Italian CCS scenario for the cement industry. And so we investigated 3 cement plants in the northern industry, not only Vernasca, but also Buzi Unicem Ropilante and one Ital Cementi Kalushka Dada, which is located in the region and very close to the storage site. So this is model. And we choose one, the cheapest to make one of 3 scenarios. We choose to make techno-economical modeling for 2 cement plants. One of these Buzi Unicem Vernasca and another Heidelberg Ital Cementi Kalushka. And we estimated costs. And so, for example, CO2 transfer storage and monitoring cost is 15 euro per ton CO2 for Vernasca, explained by 4 times longer pipeline distance and needed CO2 compression. But for located 34 kilometers cement plant from storage site, the cost for only for transport, storage and monitoring will be 4 euro per ton CO2. Concerning capture costs, the aim of the clinker project was to reach a very good price, not higher than 25-35 euro. Initial estimations of calcium looping capture costs published in 2019 is 58 euro per ton CO2 avoided. So the maximum cost, total cost, if we take this 58, will be 73 euro per ton and 75 euro per ton. But the real cost, which I accept to be 2 times lower than this 58 euro, will be estimated at the end of the project. I can't report now, because also now there is in the Vernasca, there is a process of changing fuel, and therefore all numbers will be recalculated for capture costs at the end of the project in the final reports. And we also had the task for mineral carbonation first, mineral carbonation of different waste materials, and we made experiments of different materials, and the best material which we studied in experiments, it is Estonian oil shale ash, which is produced during use of Estonian oil shale for energy production. So the experiments were made in 46-liter reactor, and the pilot testing at Vernazka will be in 200-liter reactor. So generally, this is experiments already at the Vernazka pilot testing equipment for 200-liter pilot. And we also are very active in dissemination activities. This is our Estonian dissemination activities in media, in newsletters, printed, internet newsletters. And this is our dissemination activities to our parliament members and to ministries, Estonian ministries. And this is dissemination activities of our Italian coordinators. This is Martina Fantini, our coordinator. I would say that professor, two coordinators, technical and official coordinators from Italy, and they're very active in dissemination and communication also, in Italian level. And I think that I have all my time. So this is, of course, the project which received money from European Commission through this grant agreement. Thank you very much.
Thank you very much, Alla. And I love that we already have a competition for transport and storage costs just in our webinar today. This is excellent. So it just shows that we thrive on competition.
Yes, I have to say that we have this competition started some years ago during our Baltic Carbon Forums. We have an annual Baltic Carbon Forums every year. Of course, it was sometimes in Tallinn before COVID, but last year during COVID it was online, and this year again online. And in maybe in 2018 or 2019, when it was in Tallinn, also, of course, always we have presentation from Northern Lights project. It was before they called it Longship. And Northern Lights, from the beginning, showed us a map where they are planning to transport CO2 emissions from all Baltic states, from all countries, including UK, Netherlands, France, everything, to Norway. And even several years ago, we started this discussion, and that I would say that many Baltic stakeholders were not happy, and that because if we make storage in our Baltic region, Baltic states, so the costs will be at least 2 times lower, or maybe even. And today, this was proved by this number, which we got from Paal, that only storage part will be 55 euros. Thanks for attention.
Thank you very much, Alla. That was an excellent presentation. Really good to see another innovative CCS projects coming and hubs and clusters developing, as we all know that they need to. So we now move on to our next speaker. You to have a quick look at those, and maybe we pick them up later if we need to. But otherwise, Ishtar, I'd like to invite you to take over the screen and to please give your presentation.
Thank you.
Sarah, I think you need to stop sharing.
Yeah.
Thank you.
Okay, thank you. Can you see my presentation?
Yeah, there we go. We can now see your presentation.
Okay, great.
Okay, great.
Well,
the floor is yours.
Okay, thank you. So I'm going to give you an overview slash update of the Gorgon carbon capture storage. So my name is Ishtar Barranco. I'm a geologist by background. I worked for 10 years in the Gorgon CO2 injection project as a lead geologist until 2018. And I have been working since then in the digital technologies. A lot of the digital projects that I'm working are involved in CO2, mainly in the part of acceleration of geomechanical, induced seismicity forecasting, surveillance dashboards, and things like that. I guess most of you are familiar with the Gorgon CO2 project. It's been all over the place for many, many years. So the Gorgon project is a subset of the Gorgon LNG project, which is located northwest shelf of Western Australia. This project gets the gas from two giant offshore fields, the Gorgon Jansz and the Jansz field. The Jansz field is low in CO2, the Gorgon is higher on CO2. So the gas is then processed in Barrow Island, which is 60 kilometers offshore of Australia mainland. This is a project that is operated by Chevron, but it's a joint venture with Exxon, Shell, Osaka Gas, Tokyo, and JERA. And we also receive for this project 60 million funding from the government of Australia. The Gorgon LNG plant commenced gas processing in 2016, and we started the processing using low CO2 content gas. There was some delays in the construction plan, so it was decided to focus the effort. We have a lot of restrictions, as you may know. Barrow Island is a Class A reserve nature, so we have very limited land take and a lot of quarantine and other kind of restriction of working on the island. So as a result, there was some delays on the construction phase. So it was decided to start train 1 with Jansz, which was low CO2, which caused some delay in the construction of the CO2 separation part. The Gorgon gas field was start supplying LNG in 2017, and the initial intent was to have the CO2 injection system available from the startup of the Gorgon field. And the idea for this is because the Gorgon field is higher, so in CO2, so Jansz is about 0.2% of CO2, while Gorgon is between 12 to 16% of CO2. So sorry?
Sorry, Roman is speaking. Roman, please mute yourself. Thank you.
So the idea was to start with the Gorgon field. However, there was issues identified during the pre-commissioning work that highlighted the potential concern during the non-standard operation, because normally water vapor control was expected to be maintained with a safe operating margin during normal compression operation, but this during the pre-commissioning, it was shown that in some cases this cannot be guaranteed, and that the liquid water could condense during the compression during offset conditions. So as a result, there was extensive upgrade that was performed in between 2017 to 2019 to install a Joule Thomson cooling system, the DexPro-TM, to reduce the water content of the CO2 stream. These modifications were made to each of the 3 CO2 compression trains in series that were completed between August 2019 and February 2020. The injection of the supercritical CO2 for the first remediated compression train began in August 2019. The full capacity of the 3 train CO2 compression and injection was available in late 2020. So between August 2019 and January 2021, more than 4 million tons of CO2 were injected into the Dupuy Formation beneath Barrow Island. In this moment, we have already injected more than 5 million tons in the Dupuy Formation. This schematic shows the different part of the system, from the offshore gas condensate fields, the LNG plant with the 3 acid removal units, the 3 compression trains where the supercritical CO2 is compressed and injected at 190 bar and 60 degrees Cs. And it also showed the pressure management system, which comprises of 2 drill centers with 4 water producers and 2 water injectors, with a basis of design rate of 60 to 80 kilobarrels per day. The idea of the pressure management system is to manage the Dupuy reservoir pressure, because this is an aquifer that has not been depleted. So we need, and it's a limit it's not that infinite aquifer, it has some limitations. And because we are also talking about lower permeabilities, we need to be managing that pressure. The CO2 injection system is consists of 7 kilometers of bored pipeline, 3 centers with 9 CO2 injection wells. The basis of design rate for the is 220 to 250 million scarf per day, so about 4 million tons per annum. The early CO2 injectivity has been shown as expected. We are having about 200 million scarf per day injection once we got the third compression train in there. The initial development plan was approved in 2009 when we have the environmental approval zone and the FID. And as I mentioned, it consists on 3 compression models with a 7 kilometer long 12-inch pipeline with 3 CO2 injection wells or drill centers and 9 CO2 injection wells in total in between those 3 drill centers. It also has the 2 pressure management wells, drill centers, which has the 2 water producer plus 1 water injector per drill center, and we also have 2 purpose drill reservoir surveillance wells. We also have a well that was drilled in 2006, which is called the data well, because that was the only well that penetrated the whole Dupuy formation and that we used to collect a lot of core data. We have 500 meters of continued core, including the seal, and lots of geomechanical, geochemical, and reservoir testing was done with that core, which was the one that was used as for the initial modeling and development plan. The compression models are within the LNG plan and were installed as part of the overall facility construction. The CO2 pipeline was installed in a 7 kilometer trench at a depth of approximately 1.5 meters. That is to maintain the temperature constant, because Barrow Island can get really hot and sometimes really windy. And the pipeline was designed to be big at regular intervals. Each of the CO2 drill centers, A, B, and C, has a system of manifolds, piping, chokes, and valves, along with a vent for each well. The pressure management sites are located remotely from the CO2 injection pipeline, and they have the power control system to support the electric submersible pumps in the water producers. The 2 water production wells at each drill center are manifold to have combined injection flow into the water injection, which is completed in the overlying Cretaceous Barrow Group. So this is showing a stratigraphic section of Barrow Island. The CO2 injection interval is the Dupuy Formation, which is a sandstone-rich formation deposited during the late Jurassic, not long after the Barrow Reef was formed when India and Australia were separating. The Dupuy Formation has a thickness between 200 to 500 meters of massive sandstone and highly viturated siltstones that are interpreted as deposit on an unstable sandy slope dominated by gravity-driven process, including high and low density turbidites and mass transport deposits. The Dupuy Formation consists of a channelized slope to base of a slope deposits, which was deposit on a raw submarine gravity slide with pressure waves and topographic lows, which were infilled with better reservoir quality sands. We have a fine grain sand sequence, which was deposited about those transport infill section that has variable reservoir qualities with permeabilities below 0.1 millidarcies in the viturated zone. So that's 0.1 millidarcies is within the viturated zone and the debris flow. And then we have permeabilities of up to 200 millidarcies in the turbiditic sandstone. On top of that lower Dupuy section, there is a more massive unit that is called the upper massive sand, which was deposited as it's cleaner, but they have a bit thicker chloride coatings, which resulted in lower permeability below 100 millidarcies. Above the upper massive sands, we have approximately 100 meters of viturated silty deposits, which is a waste zone that helps to slow down the CO2 migration before arriving to the first sealing unit, which is the basal Barrow Group shelves, which is a Cretaceous shell. On top of that, we have the Barrow Group, which is an early Cretaceous progradational succession deposit over 8 million years, reaching a maximum thickness of almost 2,000 meters. At Barrow Island, the Barrow Group deposit begins in the base Barrow Group shell, which is our first seal, and then shallow up and coarsening up to a multi-darcy coarse grain sand, which is the upper Flacor formation. The base Barrow Group shell is the basin floor mudstone, while the mallow well formation are the bottom set, and the Flacor formation is the top set progressional succession. On top of the base Barrow Group shell, we have an intermallow well seal, which is our secondary seal for the CO2, and above that is the mallow and the Flacor. The water disposal part, because we are in a class reserve nature, we are not allowed to dispose the water that we are producing from the Dupuy. So we have to dispose it in the Barrow Group, and that is deposited in the upper Flacor formation and in the whole Flacor formation, but the upper Flacor formation is the one that is taking almost 80% of the injectivity because of the multi-darcy permeabilities that we have that. And that's the reason why the design is 2 water pressure management from the Dupuy, where we have milli-darcy permeability, and 1 water disposal wells where we have multi-darcy permeabilities. Sorry. The drilling campaign of the CO2 started in 2013. The 17 wells program was completed within 2 years. In addition to that, we also have in the past acquired 3D seismic in 2009 that was used for well planning. We use that seismic to select the targets, and then we integrate that data with the data well that was drilled in 2006. That create the models that was used for FID, and the drilling campaign of this new 17 wells showed that we were within a very close to the predicted P50 or best case geological scenarios. Since we are working in a class A nature, the 9 CO2 injections and the 2 reservoir surveillance wells have to be drilled from only 3 drill centers to minimize land footprint. And in order to avoid interference between the wells, those wells are 7 of the wells are deviated and 2 of the wells are vertical. The 2 surveillance wells are deviated and located in a position between the CO2 injection wells and the pressure management wells in order to calibrate the models and to improve the CO2 plume forecasting. The wells were drilled in a sequence to maximize early data collection. As I mentioned before that, we only had the data wells, so we wanted to reduce the uncertainty drill center C and A. So we drilled the first 2 wells from there in order to decide the final number of wells that we will have in each drill center. And we have a very comprehensive data collection that was include logging suite, waterline, pressure testing, rotary sidewall cores, full core. We acquired full core in the 2 surveillance well, 210 meters of core. All that with the idea to reduce the uncertainty, not only on the reservoir quality, but also on the rock mechanics properties. The wells were designed to ensure high quality cement job across the reservoir and seal intervals. And we run cement logs to demonstrate the good cement. All part of the system, which were exposed to CO2, were completed with 25% chromium tubular, which allowed the contingency of future flowback of the wells in case of injectivity degradation. So after the success of the CO2 drilling campaign, the drill moved to DCD and E to drill the pressure management wells with the 2 deviated formation wells for water production and the vertical well in the Barrow Group for the injection well. In 2015, the drilling rig was demobilized and the final completion work was done utilizing a smaller workover rig. The final well completions were completed in 2017 in preparation to start CO2. All wells were completed and cased and perforated. The CO2 injection wells were perforated across a gross interval of around 300 meters, and the wells were then cleaned up with nitrogen lift flowbacks to water tanks. The pressure transit analysis of the built-up data after the flowbacks indicated very low skin numbers and KH in the near wellbore region of about 5,000 to 15,000 millidarcy meters. The pressure management water production well were selectively perforated to avoid lower strength sand to minimize the risk of sand in production. As you can see in this slide, all 9 CO2 wells injection encounter reservoir geology close to expected, both in quality and thickness. A significant amount of rock mechanic testing and geomechanical modeling was done since the early stage of the project. We have early models based on the limited data that we have from the Gorgon data well and the image logs in 2006. So collection of geomechanical data was a key focus during the formation evaluation program during the drilling campaign. We acquired borehole image logs across the Dupuy formation in all the CO2 injection wells, in the reservoir surveillance wells, and in the water producer wells. We also have image logs in the Barranco group in at least one well per drill center, and for the whole overburden section in the DWI-1 well, which is the water injector wells in drill center D. We have cross-dipole sonic was also acquired in several wells and per drill center, and we acquired also FIT, LOT, and XLOT data during the drilling campaign. Whole core was taken in the 2 surveillance wells. We have 146 meters in CRS2 and 46 meters in ARS1. Rock mechanic testing was a key focus for the core analysis to reduce the geomechanical uncertainties, and we also acquired 35 Excel rock large rotary sidewall cores in the injection well DWI-1, targeting the overburden formation ranging from depths 300 meters depth to 1,600 meters depth. So we have the whole overburden up to the Barrow group. These samples were taken from different lithologies and different rock mechanical properties to help calibrate the 3D mechanical air model in Barrow Island. And this was integrated with legacy data to update the 1D and the 3D mechanical air models. The monitoring and verification plan was submitted in 2009 as part of the project approvals, and it was updated in 2014 to align with the current technology and with other CCS projects. Lessons learned from INSALA were applied, and the Quest M&B program was used as a benchmark, as was presented before. We also used the bow tie risk assessment process to rank technologies in terms of the ability to reduce project risk, either as a preventive measure or a diagnostic tool, or to minimize the potential negative impacts. The primary method for monitoring CO2 movement is for the seismic. We have a 2009 baseline seismic survey, which is still valid. For the longer term repeat surveys, is high resolution. However, the acquisition method of a large cable-based receiver array has been overtaken by the advent of autonomous node technology. So in 2017, a pre-injection node survey was acquired that covered the vibro-sized area of the original baseline. It used a similar acquisition geometry of receiver and source line as the baseline seismic survey, but we reduced the spacing between vibrator station to overcome any losses from the reduced geophone density. By removing the need to deploy cables, it significantly reduced the workforce safety exposure in the field. The final product was very good quality, and it will now be the baseline data sets for the initial repeat surveys. The first repeat surveys is being acquired as we speak. In addition to the change in the 4D seismic program, the updated MME plan included the use of INSAR technology to measure the change in surface elevation in order to help us track the distribution of reservoir pressure. The data is acquired at least weekly, sometimes more than weekly, and the time slide process data delivered every 6 months. The pre-injection data has been purchased and processed for baseline data. We also have basic monitoring included into the updated MME plan. The data well was converted into the above zone monitoring well, and the Dupuy section at the bottom of the well was cemented to prevent leakage from CO2 as it migrates through the past the well. We have 4 station multi-component geophone array installed in the well in the Barrow group above the Dupuy. In addition to the downhole array, a pilot system was installed in the southwest of the data well utilizing legacy buried geophones. And the objective of that was to test the signal quality compared to the high fidelity downhole array. Acquisition commenced in 2017, so we have more than 2 years of pre-injection baseline data. The veracity of the near surface data has been proven, and the passive microseismic array was recently upgraded with a purpose to design it to set the receiver location. The data well was also utilized to create an above zone pressure monitoring location. So the whole section above the Dupuy was perforated and a downhole pressure gauge was installed. The reservoir pressure within the Dupuy Formation is being monitored in real time by permanent downhole pressure gauge in 8 of the 9 CO2 injectors. The follow-up data obtained when wells were temporarily taken offline has proved very useful for history matching of our reservoir models. Other monitoring techniques included in the plan are the case hole saturation log, the BSP, and the two surveillance wells, and the near surface groundwater and salt gas monitoring, including with the satellite vegetation and health data. This is the last slide. There's a lot of things that has been going around. So the CO2 injection commenced in August 2019. And since then, more than 5 million tons of CO2 has been injected into the Dupuy Formation. The CO2 from the first compression train was pumped into the AI2 well, injection wells on DCA. Once the pipeline section up to DCB was reached 50 degrees C, the well BI6 was opened, followed by AI1. Then when the complete pipeline was sufficiently heated, CI7 and CI8 were opened. At this time, the average injection rate across the field was 41 kilograms per second, so about 67 million scf per day. The remaining 4 wells, BI3, BI4, BI5, and CI9, were first started up between early to mid-September in preparation for compression model 2 startup that happened in October 2019. This took the daily injection to 90 kilograms per second, so above approximately 149 million scf per day. The third compression train commenced CO2 injection on 26 February 2020, which took the daily injection rate as high as 150 kilograms per second, which is about 245 million scf per day. As the CO2 injections were progressively opened up to flow, we have step rate tests conducted while monitoring the pressure at the well and the downhole pressure through the gauges. After the second compression model startup, the additional CO2 volume allowed testing of each well to a maximum design rate to prove injectivity. Additional interference testing involved conducting pressure fall-off tests where different wells were shut in while monitoring the pressure response at offset wells to understand the potential overlap of drainage area between wells and drill center. Finally, the pressure gauge installed at the electric submersible pumps on DCD and E, which are where we have the water producers, were closely monitored to identify the timing for the pressure response created by the CO2 injection, which ultimately confirmed lateral continuity and hydraulic connectivity across the reservoir. Pre-injection well performance forecasts were made for key dynamic parameters. The observed rate of increased reservoir pressure was lower than predicted, which required an adjustment on the modeling parameters to obtain good history match. The pressure pulse arrivals time at DCE confirmed a mid-case reservoir connectivity forecast. The other major elements of the CO2 injection is the active pressure management system. This system, as I mentioned, consists of 2 drill centers with water producer and 1 water injector wells. These were supposed to be online when CO2 injection commenced. However, there was an issue with solids production from the water producing, which interrupted the water injection in the Barrow group, which delayed the startup of the pressure management system. This issue has been rectified now, but that's the issue that has been in the news for a long time. So the problem is not CO2 injection. The problem was with the water disposal element of the system. The intent of the pressure management system, as I mentioned, is to provide the long-term of the control of the reservoir pressure by offsetting the reservoir volume of fluids injected by the CO2 injection well. The effect is not instantaneous, so that's why we were able to continue injection of CO2 while the pressure management was not online, but it allows some natural dissipation of the new well pressure increase. Despite the delayed startup of the pressure management system, the Dupuy pressure remains within the basis of the site operating limits. So we are below the frac initiation pressure, and it is expected that it will continue within the same basis once remediation of the pressure management system is complete, which is already now. So we are already producing water and injecting into the Barrow group. The early CO2 injection performance has been excellent so far, with flowing bottom hole pressure lower than originally expected from modeling. The first repeat case hole saturation from ARS1 and CRS2 when as expected, and it showed no presence of CO2 in either of the surveillance well, which is what we expected. Also, the INSAR data has, we also have been already acquiring INSAR data, so it has been processed every 6 months. The data that we got in August 2020 show a maximum uplift of 5 millimeters in the region of the CO2 injection. The passive monitoring system began detecting microseismic event in September 2019. So far, at the time, the largest magnitude recorded was 1.1 magnitude, which is more or less than what can be found really in surface. The monitoring data, all this monitoring data has been used in conjunction with the mechanical and reservoir models to history match the simulation and geomechanical modeling. So the Chevron and the Gorgon joint venture participants will continue to monitor and optimize the performance of the CO2 injection system with the focus of the long-term and safe and operation over its 40+ year life. So this is so far the update. If you have any questions.
Thank you, Ishtar. That was a really good presentation. I really enjoyed the detail, and it's great to see CO2 in the ground. I'm always in favour of practical projects that are actually getting the job done. So this is wonderful. Thank you very much. We have one very quick question that I'll ask Ishtar to read, and then I'd ask that if you could have a look at the questions in the chat as well, because I'd like to allow us a short comfort break. So we had a quick question about the water injection. Can you elaborate why this is not the primary CO2 injection target, and what was the impact on the storage costs? You're muted, Ishtar.
Sorry, I was trying to just by including water product. Can you? Oh, okay. So the reason why we have water production wells is because this is an aquifer that has not been depleted on that, and the basis of design was that we will be injecting CO2 below frac pressure, and also by producing the water. So by producing the water, we ensure that the reservoir pressure doesn't exceed that limit, and also it helps us to optimize the injectivity. Because as the pressure in the reservoir increase, your injectivity reduce, and then you have a limit of the maximum pressure that you have in your your system of your CO2. So there is a point where your pumps cannot pump at a higher pressure, and at a moment where your rock cannot continue holding without breaking in that. So that's the reason why we have to put water production wells in there. So, and the basis of design was based on a P50 case scenario on the number of CO2 versus pressure management that we needed to ensure injectivity was with those 9 CO2 wells within the base of design of this, how much CO2 we will be producing from Gorgon at the time.
Okay, thank you very much, Ishtar. So I see there are some more questions for you and Sarah in the chat, but I'm going to suggest we have a very, very short comfort break. So if everybody could please come back for 4 minutes past the hour, with being that brutal, that would be wonderful. So please have a quick break, and we will see you in a few minutes. Thank you, everybody, and thank you very much to our presenters from the session. That was a fascinating group of talks, and thank you so much for your enthusiasm. Hi, Don, you made it.
Hi, Ceri, yeah. So managed to get in fine, so that's good.
Yeah, we had a few connection problems yesterday and a couple this already today, so it's good that you made it in time.
Yeah, no, that's fine. Yeah, it was interesting, that update on Gorgon. It's good.
Yeah, very encouraging. How are you doing?
We're doing well, yeah. So lots going on here. CCS is really there's a lot of interest developing in Alberta. So I think Rick gave an update yesterday, right? So
yeah, it all sounds encouraging. As I said, I'm all in favour of projects that are getting CO2 into the ground.
Yes, yeah.
A few years ago, we wanted to have the title of the open forum as "Just Do It," but we felt that was already trademarked.
Yes. So then Nike would have been after you.
They would.
Yes. Yeah. How's your site coming along? Is that getting close there?
Yes, we think we've resolved the problems with the injection kit, so that's very promising for the site. We now need to carry out some additional testing and get CO2 into the ground, make sure we've got everything in. We're installing the water level sensors before injection, so they arrived a little bit late, but we're going to get those on site, and then hopefully we should be ready. We're looking for CO2 injection probably May next year, but we want to do a little test sometime in the autumn, we hope, just to make sure everything is actually going as we think it is.
There's always surprises, so.
Oh yes. Yeah, there's a big difference between a desktop study and getting CO2 in the ground, which is why I get so enthused when I hear lots of people talking about, even if they've just got, just started just getting a little bit of CO2 in the ground. I'm like, yes, come on.
Yes, yeah. Can you hear me okay? I actually didn't bring my my headset. I'm out of town at the moment.
Yeah, you're very, very clear.
Okay, good.
Oh, you get the unenviable slot of just after the break.
No, that's okay. Yeah. It's recorded anyway, right? Is that recording going to be available?
Yes, we're going to make the recording available after the event. We're going to email all of the speakers and ask for permission to share slides from the recording, just to make sure everybody's really clear. We did send out a warning ahead of time, but it's just to make absolutely sure everybody's really happy with everything that goes online, because we've already had, for example, a modified presentation from somebody.
Okay.
And a request from one of the speakers to omit their recorded session because they haven't got some of the permissions.
I see, yeah.
Okay, so I think we're at 5 past now, so I'm hoping that everybody's back and refreshed with a fresh cup of coffee or whatever your preferred hydration method is for the afternoons. So I'd like to welcome you to the next session, and I'm looking forward to some exciting presentations about contributions to monitoring storage potential and risk assessment. And the first speaker is Don Lawton from the Field Research Station in Canada. So Don, the floor is yours. Would you like to share your screen?
Thank you, Ceri. I'll share my screen here. Just confirm that you can see that okay?
Yep, we can see your slides.
Just go into show mode. Yeah, so good. Good afternoon, everybody. It's actually morning here in Alberta, and very pleased to be able to present to you this morning an update on our field research station in southern Alberta. And I'll just move directly into, this is really put together by our team here at CMC, combined with the University of Calgary and many of our other international collaborators, all working with us at our site. So really the main goal of this this facility is to look at the detection threshold of CO2 for a variety of monitoring systems. And what we see here on the right is a photograph of our field facility. We have a CO2 storage tank, a condenser. The CO2 comes out of the tank through a liquid CO2 pump along a discharge line into a heater and then into our injection well. And here we're injecting relatively shallow at a depth of 300 meters. So that's shallower than what would normally be looked at as for storage. But the analogy here is that if there was a upward migration from a deep sequestration site, how quickly could we determine that leakage with monitoring technology? So rather than having CO2 coming up from below, we're actually injecting from above into that same depth. At this stage, we've injected around 42 tons. So again, the objective is not how much we can store, but how little we can detect. So I'll walk you through some of the results we've achieved over the last few years on temperature, ERT, VSP, surface seismic, and microseismicity. So these will just be very highlight-oriented slides, so it won't take too long. So we've been doing some really interesting results coming out of our injection well temperature. Because the reservoir permeability is actually quite low, we increased our bottom hole pressure upwards of 5.5 to 6 MPa, And even though we're relatively shallow, at 300 meters, at the reservoir temperature, which is around 12.8 degrees Celsius, we actually do form a liquid column of CO2 in the base of the well. And what we were doing is we're injecting twice a week for a day at a time. So on these slides, just two different perspectives, you see this is the temperature in the injection well from the near surface here down to the base of the well at 300 meters. So here's an injection period here for a short period of time. This is time axis here, and here's another injection. So here's just a looking down view upon those temperature profiles. Blue is cool and red is warm. So you can see the temperature gradient in the well when we're not injecting increases toward the bottom. We have liquid buildup, but what we see is a sudden temperature drop at the base of the well. This is measured on DTS fiber on the outside of the injection tubing. So we're seeing Joule-Thomson cooling occurring as we inject from the base of the well into the reservoir. We'll come back and discuss that a little bit more later. But what you also see is that in this slide here, you see these diagonal lines. This is actually the gas liquid boundary as it decreases in the well. So we're seeing some local cooling at the interface between the liquid and gas phases. So we're doing a lot of work on temperature as a monitoring technique actually for this situation. For the electrical resistivity thermography, this has been very successful in terms of early detection. So we have an array of 112 electrodes along the surface over a trench 1.1 kilometers long, and then the injection well is shown on this slide here in the center. We have two observation wells, and in the geophysical observation well that is 20 meters away from the injector, we have 16 electrodes that straddle the injection zone. The other well is used for geochemical observations, and we also have geophones and fiber in both these wells. So we've been injecting and running an ERT survey every day for the last several number of years. And this work has been done by Marie Mackay, our researcher, and in conjunction with groups from Connie from GFZ has been working with us on this. So here's some results, just of processed resistivity data using a baseline that was starting in September 2019, where only a small amount of CO2 had been injected. So we see here the resistivity ratio after the end of October 2019, where only 1 ton of CO2 being injected. We can see a slight increase here. So this distance is really distance away from the injector well. So the observation well is sitting at this location at minus 19 meters. And as we later time, April 2020, October 2020, and then April 2021, we see that the resistivity ratio is increasing across our zone. What's interesting, we just go to the one in April, we see the highest resistivity ratio occurring slightly above our injection zone, which is sitting down at this zone here. So we are seeing a little bit of upward migration of CO2 into a coal zone that lies just above our reservoir. And that's overlaying that is a shale that we don't get any further migration up there. But we're really seeing a nice image of the CO2 plume as it reaches the observation well. And we lose resolution because the ERT array is in the observation well, so we don't see it as clearly coming from the injector. And if we convert that to CO2 saturation, this is the outcomes that we see through to just April of 2021. Saturations of upwards of 5 or 6% CO2 close to the observation well, and again losing resolution as we move further away. But we do see some CO2 at the upper level of our injection zone, but the largest changes in this coal zone sitting above our injection zone. So that's the update on ERT. For time-lapse seismic imaging, we're doing a lot of work with BSPs. So this map on the left shows our array. Our injector well is red. This is the observation well on which our geophone array is sitting. And we have both fiber and geophones in the well. And we record these series of BSP offsets every 3 months or so. And here's just an example of looking at the time-lapse difference of processed BSP CDP walkaway sections On the right here is the difference section between March 2021 and May of 2017. So you can see the difference section is quite noisy, but we are seeing between the injector and observation well number 2, so this zone in here, a change in the residual amplitude of the injection zone, which is the Spatial Valley River sandstone, and we see events sitting below that, which we interpret as being slight time delays caused by injection into that reservoir zone and the upward migration into the coals. Net time difference based on forward modeling is less than about 1 millisecond. So we're in the sub-millisecond time difference, but a small amplitude increase in the residual here, which we interpret as really just being able to see the CO2 as it's being injected now. So we're just right on I think the limit of detection threshold for CO2 at this amount of around 20 tons that have been injected at this time. At the site, we have around 5 kilometers of optical fiber installed, and this is a cartoon on the left showing the fiber. It comes out of our on-site trailer, goes into observation well number 2. We have both helical wound and straight fiber. The straight fiber in the observation well number 1, and then a fiber of both types in a 1.1 kilometer long trench. So on the right, just example shot gathers from an interrogator output from a survey done with a large vibrator source in 2020, and then a smaller source in 2021. You see they're quite similar. So these V patterns you see up shallow are the fiber loops in the wells. These 2 are in observation well number 2, and this is an observation well number 1. And then we're really interested to see whether or not we can detect reflections on the fiber that's buried in the trench. So these are just 2 examples of gathers over that 5 kilometers of trench data. We're currently working up the trench data, but we've done the walkway processing of the well data currently. And some work one of my postdoc, Jishan Wang, has been looking at 2 data sets. We have one line 15 shown here, and then a walk around series of shot points. And if we just process these through to corridor stacks, this just shows the differences between September 2020 and March 2021. In this case, using 2 different interrogators for 3 example shots from this walk around survey, and then the VSB CDP section from along line 15. And we're just currently working on the differencing on these, but looking at detail at the outside corridor stacks, we do see a time delay of about just under 1 millisecond across the reservoir zone between the 2 surveys. So we are starting to see that both in terms of reflectivity and time-lapse changes. Recently, we, in a collaboration between acquisition company here in Calgary, Stride out of the UK, and CMC, we just repeated our surface seismic survey, but using these nodes from Stride, a very high density survey. We had a 7.5 by 7.5 meter layout of receivers. So there's around 20,000 nodes were laid out over this 1 square kilometer, and we ended up recording about 15,000 shots with a proprietary Explore source into this array. So huge data set, around 250,000 traces. No, 250 million traces were acquired, which we're currently just processing. Just some of the interesting things that you see when you have such a large array of receivers. This is the RMS amplitude of the Stride nodes. So these are recording continuously for the entire survey, which it took about just over 2 weeks. We see some interesting background amplitude variations just in the actual passive data. You can see where there's a couple of pipelines here, we have fewer receivers. So this is on the receiver side here on the left during Viber size operations, which we also ran a Vibe survey in addition to this proprietary pinpoint survey from Explore. And then with the ability these days to record noise, we're able to look at the source related noise during acquisition times. And on the pattern of Explore source points here, the blue colors indicate days that were quite windy. So we're seeing responses of different noise levels. So these data are currently being processed, and we'll be able to discuss these probably by next year. We have been recording microseismicity continuously for the last 2 years, and the postdoc Jannicke, who actually just has left us and gone to a new postdoc position at Geneva, has worked on the microseismic response. Because we're so shallow, we are actually recording tens of thousands of events, so being able to separate those that are due to injection from just background noise has been one of the big challenges. So Jannicke and our microseismic team have been looking at a whole range of different analytical methods to separate these, what might be injection-related events, from background noise. And this just shows a couple of examples. In this case, this is looking down on the site. So we have 27 permanent recording surface geophones here, 3-component geophones, out to offsets of about 500 meters from the wells. The wells are clustered in the center. And then this is just a vertical section in the north-south direction, and this is an east-west section showing the interpreted event locations using non-linear probabilistic methods for the analysis of the microseismic data. So what we have seen in this approach is a lot of events up shallow. These were recorded over this springtime, and here in Canada, that usually is associated with some thaw cycles after winter. So what we're seeing really is a geomechanical response, I think, over that spring period. We've been now doing a new technique she's developed known as coalescence mapping. So this just shows, again, the plan view, showing the location of events in plan view, and then on vertical sections through the wells here north-south and east-west. We're seeing a smattering of events into the deeper section and some around our injection zone. So now being able to start to separate the events that we interpret to be related to injection from those that are just background cultural noise. We've also been looking at microseismic continuous recording on DAS. So this, we have our own interrogator. We have a partnership with OptoSense. So what we show here is just some of the surface noise that we can record, because we have a lot, say, trucks arriving on site or other near surface activities. So this is again, our 5-kilometer array of DAS data. So here are the well data on the left side, and then here's the microseismic, or at least the results from the fiber sitting in the trench. And this is a recording of about 40 seconds worth of data, showing when there was actually a vehicle arriving on site. You see it on the fiber, that's in the horizontal trenches, and see when the truck reaches the facility and stops. So being able to record a lot of this ambient noise, and then starting to use with some of our team ambient noise correlation methods to understand, to look at changes in the velocity structure. And that's something we've been working on for the past year or so. So you probably saw this from Rick Chalturnik yesterday, but there's a huge amount of interest developed in CCS here in Alberta, and the provincial government has just released a call for the development of CO2 sequestration hubs. So the monitoring systems that we're testing at our site, as well as monitoring systems from elsewhere, will now be critical to monitor these hubs as they develop. So this concept is having a hub operator who will take CO2 from a variety of large emitters, and they'll be responsible for sequestration in a number of hubs around the province. And probably thought that we could see upwards of 6 different hubs. If we want to get to gigaton storage, then each of these will be large sequestration systems. So that's really an exciting development here in Alberta, of getting more CO2 into the ground. As I mentioned at the beginning, we are seeing very significant temperature changes in our injection well, particularly as we go through the phase transitions, both in the well and also as the CO2 migrates through the perforation zones into the reservoir. We are seeing this Joule-Thomson cooling because our volumes is quite small, but we are seeing something like a 4 or 5 degree temperature drop. So we are now part of an Act 3 successful proposal known as Return, which is really looking at the use of depleted oil and gas fields for CO2 sequestration, and the concern about how you design an injection strategy when you're injecting into under-pressured zones. And so we're seeing this example for part of Act 3. We'll be doing experiments looking at these temperature changes in our wells. So that's just started, and look forward to working with many of the collaborators that are listed on this slide, and possibly some of you attending this presentation today. So that really is a quick overview of our site here for everyone, and I want to acknowledge the support that we have from we operate a joint industry project, so we acknowledge support from BP, Shell, Chevron, Equinor, Synovus, and OptiSense, which is an in-kind contributor. And we have significant ongoing base funding from the federal government of Canada through the Western Economic Diversification, and also a grant through the University of Calgary Global Research Initiative in Energy Research that enables to keep our team working and injecting programs and monitoring systems running at our site. So that, I believe, is the end of my presentation, Ceri, so I'll stop sharing at this point.
Thanks, Don. That was a really good talk, and I really appreciated seeing all of the different techniques that you're applying to answer the question, what's the smallest amount of CO2 we can find? Because
yes, I think we are close to really being able to determine the detection threshold as an early warning system for leakage from a deeper site, a traditional storage site.
Yeah, I really enjoyed the presentation with all of the monitoring techniques presented, and also the idea of noise being actually quite useful sometimes for testing out your instruments. Yes. So thank you very much for this presentation. And we'll move on to the next presentation, which is from Arnaud from GeoStock, and he's going to talk about the HyStories project. So a slight change of flavour, but something that we're looking forward to hear about, since there is such good synergy between CO2 storage and hydrogen production. So Arnaud, are you all good?
I am. Thank you, Ceri, for the introduction. Do you see my screen, and can you hear me?
Yes, I can see your slides, and you're coming over loud and clear.
Great. So thank you for the invitation. I will present you the HyStories project, trying to give an overview of the project, not specifically focused on the role that CO2GeoNet is playing here, and many of CO2GeoNet members at least. So I'm doing that on behalf of all the consortium here. So just a short introduction. So the context of the project, so it is a European funded project through H2020 framework. The context is, of course, the intermittency of renewables and their rise in the energy mix share that is desired, notably in the EU, for going climate neutral by 2050. So hydrogen is seen by many as a key element in this energy transition. And if networks are built, storages are part of networks equipments for such big energy systems. And the goal of the EU was to look at technology developments that were required for pure hydrogen storage in depleted fields and aquifers. So this is the first part of HyStories, technical development for pure hydrogen storage in porous media, which has never been done. And another thing that was asked by the call for proposals was to provide insights to decision makers, insights on storage demand per country, on impact studies if we develop underground storages of hydrogen, and case studies. So this is the second big part of HyStories. So we grouped a team to work on these topics. It includes 7 partners. GeoStock, I'm working for this company that is a probably the most global engineering company for underground storage, more than 50 years old. CO2GeoNet, well, I will not present you. The University of Leoben and the Material and Corrosion lab and department of this university in Austria, MicroPro, a microbiological lab in Germany, FHA, a foundation for hydrogen promotion in Spain, Mary from the Polish Academy of Sciences, and LBST, a consulting company from Germany. And within CO2GeoNet, as you know, it is so the association is a partner, and is here represented by 17 third parties. So many of you are, or your institute is involved. So you have the list here, and I thank you a lot for your implication in this project. I know that it is not easy, that you have to share only a part of the budget, but I really welcome the inputs you bring, and the fact that we are able to have such a large coverage of the European subsurface, thanks to your implication. Also, the project is supported by a relatively large advisory board that is essentially made of gas storage company and also gas transportation companies active in porous media storage. I will get back later on why we needed such a large advisory board. The work program of the project is summarized in this slide. So if I get back to my introduction on the two legs or the two pillars of HyStories, starting with the first one on technical developments for pure hydrogen storage in porous media in Europe. So we have broken down the work in work packages. The first one is on geological capacity assessment. So it is led by CO2GeoNet and by Ceri here as the president of CO2GeoNet that is involved in managing the project. So the goal here is to improve the knowledge that is already available, to gather it and to improve it in the target of assessing potential for hydrogen storage in aquifers or depleted fields. So this is work package 1. Another part of the project, work package 2, is trying to bring elements to one question that is looked at by several people today for pure hydrogen storage in porous media, which is mobility. It's reservoir engineering, so which is mobility and mixing questions. If we inject hydrogen, especially if we inject hydrogen in a depleted field with some native residual gas, and also reactivity and I would say mineral reactivity with reservoir rocks. The third work package is focused at interaction with microbial activity, and hydrogen can feed microbial activity. So here we will rely on an extensive test program, lab test. Work package 4 is focused on material selections for wells for hydrogen injection. So these are the subsurface technology development for hydrogen, and you may just notice that As you know, in many geology-related industrial projects, it's very site-specific. And so, and you see here that we had to come out with some tricks, I would say, to try to give answers to these technology developments in a generic way. To get a large coverage of European subsurface, we needed the involvement of a lot of institutes, and this is what CO2GeoNet is bringing to the project. To get answers on microbial activity with in contact with hydrogen, where microbial activity is is very site specific, and here again we needed samples from many different sites. I will get back to that later. So we had we are trying to give generic results here in topics that are sometimes site specific. So these are what we are doing in the technology development side. On the other side of the project, we have what we call the techno-economic feasibility studies. It starts with a work package 5 that you see here, that is based on the energy modeling of the European energy system. So for each time step, which is 1 hour, for instance, in some cases, the energy system is modeled in the EU 27 plus UK, actually. And the production and consumption of energy are matched at each time step, and it involves some transfer of energy in between member states and some storage which is introduced. And the idea here is to estimate the storage demand for hydrogen. We are also working on in work package 6 on reviewing the regulatory framework for hydrogen underground storage, and on societal and environmental impact assessments. We are also then working in work package 7 on a conceptual design of a storage site and a cost estimate of this conceptual design of a storage site. And we will use this cost estimate to rank to do a first ranking of the site and of their possible development into an hydrogen storage. And last, in work package 8, we will focus on some case studies that will be analyzed in a more detailed and site-specific way. All this aims at bringing some conclusions and some guidelines to the EU and more generally to the decision makers, I would say, for the implementation of hydrogen underground storage. So this is our work program. I will not go in deep. So I forgot to say that the project started in January this year, and it lasts 2 years. So we already worked and have some results that are essentially public and available on www.HyStories.eu. I will present you some of the work we are doing. One is one short presentation on work package 1. We had a challenge here that was to build a database of potential candidates for underground storage of hydrogen on a wide with a wide geographical coverage, Europe, and a large scope because it had to include depleted fields, aquifers, and also salt caverns. So we came out with this proposition. So we are reusing first GeoStock experience in developing natural gas underground storage, and we tried to use this experience to propose some criteria for selecting future storage sites and to give some guidelines. It uses also SMRI, Solution Mining Research Institute, GIS of soil deposits in Europe. They granted us the permission to use these results, and most importantly, we are using CO2GeoNet past works, often financed by the EU as well, and essentially done. Correct me if I'm wrong, but for a capacity estimate of CO2 geological storage. And we are using this work, and even more importantly, your ability to improve this work, to try to refocus this work and to adapt it, I would say, in the perspective of hydrogen underground storage in aquifers and depleted fields. And so all this is supposed to be consolidated in a single database, GIS, that is managed by CO2GeoNet and BGS within CO2GeoNet. Just a short, so I will not go in details into what CO2GeoNet is doing in this project. I leave this to Ceri and to project meetings. I will just say a few words on what GeoStock has done and has published for selecting a hydrogen storage site candidates. So based on our experience, we proposed scoring and screening. When I say screening, it's more than an exclusion criteria to support the selection of porous media storage site candidates. Since there is no experience for depleted fields in pure hydrogen storage, so we also used the experience of natural gas underground storage that is quite close by many ways. And we listed the criteria that we grouped into several categories: geological and reservoir engineering, geological context, and surface environments. And we, what you see on the left here is that we tried to evaluate with this scale the importance of the criteria. For the location, for the capacity, the quantity of gas that can be stored, and from the performance, so essentially the withdrawal flow rate. So this is an example of what has been done so far in this capacity estimate for hydrogen storage work package. Another example of what we are doing for work package 3. In microbiology. So as I said, microbiological activity is very site-specific, and it's hard to. We know that it's a question, it's an open question for hydrogen storage, but it's hard to draw conclusions for future sites that are yet to be identified. So what we did is that we turned to a lot of gas storage operators and asked for brine samples from their sites, not in the idea that these sites would be converted into a hydrogen storage, but in the idea that it could have been, in other words, it could probably have been selected as a hydrogen storage site. So we take brine samples from these sites as examples of sites that could have been hydrogen storage site, and we used a variety of sites. Some are depleted fields, some are aquifers, some are sandstone, some are carbonates. So we use a variety of sites to try to be representative of what could be done in the future for a future hydrogen storage site. So this is why we have such a big advisory board. A word on what we do for selection and procurement of steel for casings. So we came out with a protocol for testing steel materials, goal being to determine what steel grade do we recommend for use in hydrogen underground storage, because usual standards that are in use in the oil and gas drilling and completion industry do not cover hydrogen. So we we've done we are doing a lot of tests actually for composition of gases, pure hydrogen, and also we consider some impurities like CO2 or H2S. Two temperatures, and so at the end we have more than 56 tests that we will do for several grades. And the test, there are two big categories of test: autoclave testing. So it is put in test conditions in these reactors that you see here that are put in this room. So specimens are stressed at 90% of their maximum yield strengths to see whether if there is cracking, if there is corrosion, and also in each of these reactors there is so a specimen that is stressed and also a coupon that is analyzed there after the test to see whether there was some H2 uptake in the coupon. And another test is permeation testing to see if there is effective hydrogen diffusion in this steel. So just to say also that we had a lot of discussion on what grades are needed to be tested. We discussed it mostly with University of Leoben, Valorec, and GeoStock. So we are testing a number of materials, low grade carbon steel and also some stainless steel. And we are testing brand new materials and the impact of degraded materials. Last, another example of there's two more examples of what we are doing in this project. It is work package 5, so I'm in the other side of HyStories on the techno-economic feasibility studies. So here what we are doing is what I presented earlier, the energy modeling of Europe. So the goal is to investigate the role of a widespread deployment of underground hydrogen storage in EU 27 plus UK until 2050. So it's based on scenarios. Most importantly, the net zero emission of the EU by 2050, which is a political target we have in Europe. Then 4 scenarios were defined. Variations here are, for instance, whether hydrogen production will be domestic or imported, whether storage will be concentrated or in some countries or distributed across Europe, etc. So this leads to a number of scenarios, and for each of these scenarios, LBST has computed the expected storage requirement. So that's what we see here. So this is the estimation under these assumptions of the storage need, underground storage need, because at this scale only underground storage can answer. So to give an idea of the order of magnitude of this, for instance, assuming it is done in salt caverns with 4,000 tons per cavern, if we look at this scale, so we have between 120 and 2,500 kilotons of hydrogen that storage capacity that is expected. So it would be between 300 and 5,000 salt caverns in Europe plus UK. So last example of what is done is the regulatory framework review. So here again, it was a challenge to do this. A challenge because regulations are national and not that easy to access. So it's national, so each or not each, but we have many different languages, and even if you can read it, it's not that easy to read. You have to be quite experienced in this, in conducting this regulation, these applications for underground storage. So we have to thank CO2GeoNet members that are involved in HyStories again here, because you've been very active in helping us by answering the survey on the European, on the regulation of your country for underground storage. We also thank our advisory board members, usually underground natural gas storage operators, that have also been helpful for detailed answer for some countries that are our case studies, which are Spain, France, Germany, and Poland. So this is I try to give an overview of the project and also some view on the work we are doing on some of the work packages. I hope it can give you an overview of the project and an understanding of the project. If you have questions, please.
Thank you very much, Arnaud, and thank you for bringing in hydrogen storage and pure hydrogen storage, which is, as you say, we need to develop the technology and answer the questions to ensure safe underground storage and to integrate it into part of our sustainable future. So I would ask if you have any questions to please drop them into the chat. I see a couple have already appeared. And I will then hand over to Heike and invite you to share another project which CO2GeoNet is very passionate about. Please, can you start your share? Thank you, Arnaud. And invite Heike to talk to us about an update for the state of play of CO2 storage in Europe. So Heike, the floor is yours.
Yeah, thank you, Ceri. And thank you to all of you for, well, staying with us here at this quite late hour in the afternoon. In my presentation, I would like to show you some preliminary results of a study undertaken by CO2GeoNet on the state of play of CO2 geological storage in Europe. I present the findings on behalf of the project team that is composed of Vitladek, Alexandra Koteras, Cornelia Schmidt-Hattenberger, Jan Tveranger, Ceri Vincent, and Walter Wheeler, apart from myself. Oops. Sorry, I can't just... now. Okay. To get an overview of the state of play on CO2 geological storage in Europe, we prepared a questionnaire and sent it to colleagues in the various European countries. The questionnaire asked for information about the status of storage capacity assessment in each country. Also, we wanted to get information about current activities on CCS project planning and implementation. We asked for the extent of and focus of CCS-related research activities in each country. Also of interest were the national climate protection policies, as well as legislation and regulations relevant for CCS. And last but not least, we asked if there were any national actors driving CCS forward and about the situation regarding public awareness and public engagement activities. The focus was clearly on CO2 storage, but also we asked for related information on other parts of the CCS chain, and also touched upon the CCU activities to be able to present a somewhat broader picture. All our findings are currently documented in a report that will be available soon. Today, I will present a few selected findings as of December 2020. We managed to retrieve information from 32 European countries, many of which are represented in the CO2GeoNet Association. Those are all the countries marked here in dark blue on the map. But as you can see from this map, our study includes EU member states as well as non-member states, which is important in some respects, as for example, different regulations and obligations may apply to EU member and non-member states. In this map, you see that in most European countries, there's good to excellent knowledge about their national storage potential. This applies to all the countries marked here in green. Storage atlases or catalogs are available in a couple of countries here marked in dark green. However, these may contain rather different level of information. For example, the German storage catalog does not contain any quantified storage capacities. In the European countries, the favored storage options are saline aquifers, while depleted hydrocarbon fields are considered in slightly fewer countries. Iceland is the pioneer of in situ mineral storage in basaltic rocks. Offshore storage is preferred over onshore storage in most coastal countries. And Finland and Estonia have reported no storage capacity due to their unfavorable geological makeup of their subsurface. In all countries colored in light green, new capacity assessments or updates have recently been performed, which in our view should be reflected in the preparation of a new solid and up-to-date European storage atlas. Regarding CCS projects, there's currently a lot going on, as you see from the number of, well, puzzle pieces here on the slide and the different, all the different country codes listed here. So the activities comprise projects on the individual stages of the CCS chain, so capture, transport, and storage, but also a full chain and CCS cluster projects. The projects are in various planning and implementation stages. Still, we have in Europe only 2 large-scale CCS projects in operation. The ones in Norway, Sleipner and Snøhvit, well known, I assume, to everybody here. But there are a couple of new projects, full chain or cluster projects, in various planning and implementation stages, and those are in particular related to the current projects of common interest for CO2 transport infrastructures in the North Sea area. Capture projects and capture test facilities of various sizes are in operation in several countries, and further capture and demonstration and pilot plants are in advanced planning stages, as we have also heard earlier today. Nearly all these recent capture projects address CO2 capture not on power plants, but on industrial plants, on waste incinerators, geothermal plants, or direct air capture. In the same line, a lot of research activities on capture is on adapting and advancing CO2 capture processes due to these alternative CO2 sources. CO2 pipelines are in operation in 3 countries at present, and relatively few countries report availability of facilities for CO2 transport research. CO2 storage sites are in operation in large scale in Norway. The projects at Sleipner and Snøhvit that were already mentioned. CO2 injection is ongoing in Iceland, injecting CO2 dissolved in water for in situ mineralization in basaltic rocks, and also reinjection of CO2 from geothermal energy production is tested in Turkey. Other different storage sites are under development as part of full chain or cluster projects. In some European countries, the activities focus more on advancing the CO2 utilization instead of storage. The use of CO2 to enhance oil recovery is already practiced in Croatia, Hungary, and Turkey. The implementation of CO2 EOR is also considered in a couple of other countries as a means to kickstart a broader implementation of CCS. Altogether, all these different projects are pieces that we need to repuzzle our energy system and the production processes for the overall aim to reduce Europe's CO2 emissions. There have been a few recent changes in the national legislations in some countries, so that CO2 storage is now permitted in Sweden and the Czech Republic, where it has been recently prohibited in Slovenia and Lithuania. In some countries where CO2 storage is in principle permitted, there are, however, country-specific limitations that in some cases severely restrict the theoretically available storage capacity. So the map is in fact not really as green as it appears from the first sight. So the country-specific limitations include, for example, storage only being allowed offshore, or the exclusion of seismic and volcanic areas, or the exclusion of underground aquifers. In some countries, the state is allowed to restrict the area for storage sites or for storage site exploration. In most European countries, the awareness and knowledge of the CCS technology and its potential for CO2 emission reduction in the general public was reported to be low to very low. Please note that only for a few countries, these findings presented here are based really on scientific surveys. For most countries, the categorization shown on this map reflects the reported perception of the national contributor to our study. In some countries, the awareness of CCS was reported to be higher at stakeholder level than in comparison to the general public. Also, in a couple of countries, media coverage has recently increased in relation to discussions on the national climate mitigation strategies. Striking exceptions regarding the public acceptance are Norway and Iceland, where both awareness and acceptance of CCS are quite high to very high for various reasons. In Norway, the high acceptance can in parts be related to the government's investment in high-profile projects, such as the Technology Center Mongstad and the Norwegian full-scale CCS demo project. In Iceland, numerous public information and engagement activities by the Carbfix partners apparently successfully conveyed the message that the Carbfix technology is based on processes that also occur in nature, and that the rapid mineralization significantly reduces the risk of CO2 leakage, which contributes to an overall positive perception of this technology. Even they managed to achieve that the Carbfix technology is perceived as an Icelandic brand within the energy and utility sector. Locally higher public knowledge achieved by public information and engagement campaigns at the pilot sites in Ketsin and in Hontomin, and also around the planned full chain project in Cork, Ireland, are reported to have increased also the acceptance of the CCS technology locally. So in summary, we see a clear progress in the rollout of CCS and CO2 storage in Europe. CCS is back on many national agendas as a CO2 emission reduction technology. Also, there's been a steady increase in project numbers at various planning and implementation stages. However, still, the two Norwegian projects at Sleipner and Snøhvit are the only really large-scale CO2 injection projects in operation. The focus of activities has shifted from research and pilot scale testing to larger scale project planning and implementation. In particular, cluster projects are emerging, and many of those are related to the current projects of common interest. In many countries, capture now focuses on industrial plants and waste to energy plants, and also on other alternative CO2 sources such as geothermal plants, blue hydrogen production, and direct air capture. The public interest in CCS and the media coverage increased recently in many countries when the national climate protection strategies were discussed. Updates of national storage capacity assessments have been performed in the majority of countries, so there is a necessity to prepare a new solid up-to-date European CO2 storage atlas. CO2 is considered in a couple of countries from Eastern and Southern Europe as a good opportunity to also implement CCS on a larger scale, whereas in other countries in Europe, the prolonged oil production intimately linked with CO2 EOR operations is seen critical. So overall, there is a widespread of activities and knowledge levels across Europe evident from our study. And this points to the continued need for pan-European knowledge exchange, research and technology transfer, as well as cooperation. So if you're curious to learn more details and have some information about the very recent developments, I encourage you to read our report that will reflect the state of play as of June 2021. Finally, I would like to acknowledge all contributors to this study from the individual European countries. Without them, this whole activity would have been impossible. Thank you.
Thank you very much, Heike, for this exciting update for the state of play. I think we've heard from several speakers today who said that the temperature is changing for CCS And this is a very positive note. And I particularly like your picture of all of the pieces of the jigsaw fitting together. That's a lovely, lovely illustration for the process. So thank you for this. And I'm going to move on. I appreciate, and I apologize that we're behind time. I will have to learn how to chair more effectively. But we have one speaker that we lost yesterday and we have regained, who's agreed to speak at a horrendously awful time. So thank you very much, Darren, for your patience and for coming online today. We very much appreciate you taking the time to speak to us today.
No problem at all. Apologies for missing the slot I had yesterday. I'll limit myself to 15 minutes, and I'll just give you a rundown on the progress with the CTSGO project in Queensland and Australia. So the CTSGO project is an integrated demonstration project at this stage. There's two components to our project. The first component is the capture component, and I'll speak briefly about that in the slides today. And the second component is the storage component in the Strat Basin in Queensland, and I've got some maps to show in the coming slides. The project is currently in the final investment decision phase. We expect to make that decision later this year and move into the execution phase. So the picture you can see there is the capture plant that we're proposing attached to a coal-fired power station in Queensland. We have a very large storage site a very large storage tenement that we've been evaluating, and one of the last pieces to the puzzle is to in a world that's flushed with CO2, we can't get CO2 to save ourselves, so we have to get our own, and that's what we're building the capture plant at that coal-fired power station. There's more to just to the capture plant than just providing a source of CO2 for the storage demonstration. We also plan to advance capture technology, and we're partnered with Ceri out of China with the technology that they've got, and they've got some fairly exciting advances in CO2 capture from coal-fired power stations, and we're working with them on that. A large part of the project, however, is to verify an industrial scale storage hub in Queensland's Strat Basin, and the hub that we've got or the location that we've got is close to existing sources, but also close to potential future sources for gas to and coal to hydrogen and ammonia projects. So just a quick slide on the capture plant. The picture on the bottom left-hand side of the page there is Huaneng Ceri's Shanghai Shidongku post-combustion capture plant. We've selected that plant as a sister plant to the plant that we'll build. That plant's been in operation since 2009 and has over 10 years of successful run history. So from our perspective, it de-risked the capture part of the project for us. The technology that Huaneng can provide us is scalable. So we initially we'll build a 110,000 tonne per year capture plant, which is sufficient for us to do the demonstration project. Our demonstration project is a 3-year project. The plant itself is a modular plant. So at the end of that 3-year injection project, there's a number of potential uses for that plant. We do have the option to move it elsewhere if required, and that plant has gone through FEED and into detailed design, and we're on the cusp of starting construction of that plant. And on the right-hand side is the isometric drawing of that plant on the western side of the existing coal-fired power station. So onto the storage part of the project. We have a site in southern Queensland, so roughly 300 kilometres west of the city of Brisbane, and in an area that's fairly well explored for oil and gas. Our permit area is enormous. We've got a permit area, an exploration permit area of just under 3,700 square kilometres. It's geologically, it's an area that we've selected as being as being one of the most promising sites we thought geologically for storing CO2. We're at the bottom of the syncline in the Sara Basin. We're in the deepest part of the basin for storage. We're close to existing infrastructure, existing oil and gas pipelines and pipeline corridors. We're close to a number of sources. So we're close to a number of power stations, gas and coal-fired power stations. We're close to a number of other industrial sources as well, such as ethanol plants, and also close to the resources that will potentially be used for coal and gas to hydrogen. It's currently the only greenhouse gas storage exploration tenement active in Queensland. It won't be the first. They expect an additional round of exploration tenure release in the coming year in Queensland, but this is the only one currently active. We previously had another tenement to the north, which we explored and did a range of research activities on. We surrendered that permit. And although it looked geologically like an ideal place to store CO2, the reservoir was not saline, it was fresh water. And so it was going to be socially unacceptable to do any sort of storage in that reservoir. So I liked your analogy earlier or the example of let's do it. I probably prefer the Elvis analogy of a little less conversation, a little more action. So at the moment we're quite active in the field. In 2020, we drilled the first appraisal well on the southern part of our tenement. We're appraising a sandstone that's roughly 2,300 meters below surface. We drilled that first appraisal well. In that appraisal, we ran a range of logs and we cored the part of the seal, the entire injection interval, and the aquitard below us. The objective of that well was to assess the sandstone for its injectivity potential. We're a long way from existing well control, and permeability was our key risk. We wish to confirm the seal in the formation above us. It's a basin-wide seal, so we had low risk on that, but it was important that we did that. Importantly, we had to assess the water quality. If we were to find at that depth fresh water, that would have been the end of the project again. In a very dry continent, anywhere where the water is fresh, it's a very valuable resource. And finally, anything we do is we have a view not just for the demonstration project, but a view for any of the infrastructure we install, such as the wells, that these be capable and designed for future large-scale storage or monitoring. So the use of the size of the wells, the use of corrosion-resistant alloys, the type of cement we use, etc., is all geared around using the same infrastructure for large-scale storage in the future. Now, I'm pleased to report that well found permeability and reservoir properties that well outstripped our expectations. We've got permeabilities across nearly a 90-meter section, we're averaging 2 Darcy, and sections up to 10 Darcy. So from an injection perspective, we've got an exceptional reservoir. Fortunately, the water wasn't potable, it's saline, and it's very high in elements such as fluoride, which make it unsuitable for use without some fairly significant treatment. We were able to confirm the seal. We've got nearly 150 meters of seal, and we were also able to confirm that the sandstones that overlie the seal were in hydraulic isolation from the injection zone. So, and we're aligned here on solution trapping, so migration assisted trapping for ultimately the trap for CO2, So ultimately, heterogeneity is our friend, and we were blessed in this zone in this reservoir with heterogeneity. We've got a range of varying permeabilities throughout the reservoir section, with the highest permeability in the bottom of the section. So we're intending to inject CO2 into the lower part of the reservoir, and for buoyancy to give us the best chance of getting the most storage efficiency and storage capacity. We went back this year and drilled the neighbouring monitoring well for the injection project, and that well will serve as primarily as a monitoring well, but also a backup injection well if we require it. from a storage capacity perspective, we'll as well as the demonstration project, we're also embarking on to appraise the remainder of the reservoir across the 3,700 square kilometres at this stage, based on the oil and gas exploration data that we have in the area. We anticipate a P50 storage capacity of around 500 million tonnes that's at usable capacity in that reservoir. So the pictures on the bottom left-hand side show you the sort of country we're in. We're in large cattle grazing country, so we're a long way from community. And ultimately, with very high permeability, we're in a position where we can see industrial scale storage with very little field infrastructure. The monitoring techniques we're looking at are not dissimilar to some of the presentations you saw at the earlier session today, from Chevron and Barrow Island, for example. We plan to use a very seismic monitoring network as our primary M&V technique. We'll also have monitoring wells. On the right-hand side, you can see an artist's impression of the demonstration site. We have the injection site and the injection well and the monitoring well shown there. Those wells have both been drilled. They were drilled from a pad and directionally drilled. We've also got monitoring wells into the economically important overlying aquifers that the local community use, so that we can provide positive verification that we don't impact those aquifers. Importantly, when the project first kicked off in 2009 in the northern tenement, a lot of the techniques that we were looking at for monitoring and verification were very much research and development. Now we're able to leverage off learnings from projects such as Aquastore in Canada and the range of projects around the world. And now most of the monitoring techniques that we're looking at using are definitely well proven. So back to the pathway to large-scale CCS, the demonstration project is around proving the storage capacity and setting up a hub in that location to give confidence for industry to capture CO2, so they have a place to store it. It'll provide in Australia a reference case for future large-scale storage, demonstrate that storage capacity. Very importantly, to be the trailblazing project in Queensland for regulatory permitting, so that people have confidence to invest in the capture technology. It'll provide the foundation infrastructure for large-scale injection, and the Australian government this year set a target for storage. So that's compression, transport, and injection of less than $15 US a tonne. And that includes the full compression, transport, and storage costs, but not capture. Using the costs for our site and the assumptions listed in the box on the right. So 100-kilometre pipeline, large-scale storage, so 1 to 2 million tonnes plus per year of storage, and full compression from atmospheric up to injection pressure with project life of 20 years. We estimate the transport, compression, storage at our site and monitoring costs of less than $13 a tonne, and that also assumes worst case assumptions for power, for example. So the best case costs are less than $10 a tonne for transport, compression, and storage. So we believe that's quite a compelling case for future industry to capture the CO2 to store at the site. For the demonstration project, although we haven't sanctioned the plant build just yet, we have conducted the cut-ins of the power station so that we don't require a power station shutdown to tie in the post-combustion capture plant. The injection wells and the monitoring wells are drilled. We're about to. We've got seismic across the area, and we're about to shoot a 3D survey across the area to give us the final bit of information that we'll use as baseline information for our monitoring. We're currently in the process of seeking the environmental approvals for that injection. We expect that investment decision to happen later this year, plant manufacture to start next year, and to be injecting CO2 in commencing in 2024. I promised to stick to 15 minutes. I think I got it. So.
Thanks ever so much, Darren, and very much appreciate you coming in. And though thanks to you, I'm now going to have that song stuck in my head now, a little less conversation. So that's going to be my punishment for the evening for my lack of chairing. So thank you very much for that presentation today. And I think most of the questions have been answered in the chat. So maybe I'd just like to ask any of the presenters from today if they'd like to say very shortly what they think their project will really contribute to driving CCS forward to realise what it can do for our climate change targets. So is it reduction in costs, improving storage safety, or just proving it can be done? So do you want to say anything really quickly about your projects and how you think it's going to drive CCS forward? Darren, you're up first since you have the microphone.
First, I think all of the above. I think for me, the first challenge is to prove that, or to provide that public demonstration for acceptance so that we can do it. But the ultimate aim is around, for us, is storage capacity and cost reduction.
Excellent. I see we have a very competitive market here today. You joined a bit after the early talks, but so far we have a bidding war for the cheapest CO2 storage. Ishtar, I saw your camera come on next.
Yeah, we are not competing for the cheapest one, though. We're competing for the biggest one, and proving it can be done under very stringent conditions. I mean, when we choose this project, putting such a huge scale in a reserve class A nature complicate things on that, but if we can do it, other people can do it on that part. So it's bad.
Thank you, Ishtar. I agree. Prove it can be done. Actions rather than words. Alla, what would you like to add?
I want to add that the barriers, for example, in the Baltic Sea region, it's regulations. You could see at the map of Heike that Estonia, Latvia, Lithuania, CO2 storage forbidden. And in other countries, there are limitations. So, and of course, the costs could be barriers, but it depends where you will make storage. Closer to the storage site, cheaper storage, of course. And if all countries will look to the Norway, it will be too far and therefore too expensive, also because Norway is one of the most expensive countries in Europe. That's all.
Thank you, Alla. You're right. We need hubs and clusters, and we need a network of CCS injection and storage to really make this work. So I would like to invite Roman to have the final say today. And I'd also like to ask everybody if you could turn on your cameras. I'd like to take a couple of screenshots for the meeting report. So it would be very nice to see your faces. And Roman, would you like to say the last few words?
Yeah, I'm not going to spend a lot of time. I think what our presenters has just concluded with is an excellent conclusion. Again, I will repeat myself from yesterday and say that we see a lot of very, very practical projects, a lot of application, and that is absolutely fantastic. And with that, just see you all in Venice in May 2022. What else is there to say? With even more exciting and more industrial project applications, of course.
Of course. So thank you very much, everybody, for attending the webinar, and thank you for keeping your enthusiasm going to the end. I appreciate it's much later or much earlier, depending on your time zone. So thank you very much, everybody. And as Roman says, I hope to see you in person soon. Take care and have a good evening. Bye. Bye, take care.